Welcome to lecture 11. Today I'll talk about phase equilibria, phase transitions, phase diagrams, and equations of state, which are all connected, and I'll start with some overview. So, you all know about the phases of matter. Even at the times of Aristotle, he talked about that there are the four phases of matter, which are earth, liquid, gas, and fire, he said. But we know that fire is plasma. And you all have experience with this at conditions that you live under, at what an atmosphere. You know that when the temperature rises above 0 degrees, the ice melts, becomes liquid water, and at 100 degrees it starts boiling and it becomes vapor. And this is where we've got our centigrades temperature scale from. And we all know these phases of matter. Now I'll just remind you that the solid and liquid states of matter, they're often called condensed matter, as opposed to the gases and plasma states of matter. So condensed matter physics is about solids and liquids. And condensed matter physics is in fact the largest part of physics on a world basis. Very much because all the devices that we use have semiconductors, which are crystals, so forming and controlling crystalline phases and the properties of them is very important industrially. But condensed matter physics is a lot more, and it's both liquid and solid phases. Now, we often use phase diagrams in order to visualize, but also to show the quantification of when a substance has a particular phase. So on the axis are our state variables, in this case pressure and temperature. And a phase diagram consists of some lines which are called coexistence lines that separate, in this case, between A and C, separates gas and solid. So in order for the solid to go to the gas phase, we call that sublimation, or the other way, it's deposition. From A to B, there is the liquid-gas coexistence line. And when liquid boils, it vaporizes and becomes a gas. And when the gas condenses, it becomes a liquid. So hence the name condensed matter, that solids and liquids are condensed states. And then we've got the solid liquids coexistence line that divides the solid phase from the liquid phase. And that's where, so when the solid is melting, the state is on the coexistence line. Now, one thing that should be clear to you is that when for example, solid ice can have any temperature below the temperature here. At a given pressure, it can have any temperature. So you can heat up the solid up to this temperature, but at that point you can keep heating the solid, say the ice, but the ice will not change temperature, even though you're adding heat to the solid, because it has hit the coexistence line. All heat goes into the phase transition. All heat goes into melting. No heat goes into changing the temperature until all the solid has been melted. And this is the same for all. At a phase coexistence line, there is the phase change is connected with the heat of the phase transition. Now, there are two of these 4 points, A, B, C, and D, are really specific points. Well, C, that's absolute zero, so that's but it's not really an attainable state. But this point where the solid liquid line and the gas liquid coexistence line meet, this is a specific point. It's called the triple point because there are 3 lines that meet. So all these coexistence lines meet there, and that's a unique point in the phase space of this material. So all substances that have solid, liquid, and gas points, they have a triple point. And this point is a unique point. And also the critical point is one single unique point in the phase diagram. And the interesting thing about the critical point at the liquid gas critical point is that if you want to go from a liquid state to a gaseous state, you can change the pressure, so you can reduce the pressure and get boiling of the liquid, or you can heat it. You can take it liquid from here, from say 20 degrees, and you heat it heat it up to above 100 degrees, and it will become a gas. But then you have a phase transition. But you can also take this liquid, you can increase the pressure and increase the temperature, and then decrease the pressure and decrease the temperature, and you will get the gaseous states without going through a phase transition. Now, how is this possible? Well, the point is that neither the liquid nor the gas have any special symmetry breaking. There is no structure to it. They are both structureless fluids, so that and this is why you can go to a supercritical state and back again, and go from any point in the gaseous phase to any point in the liquid phase without going through a phase transition. And that's why there is a critical point of this coexistence line. It does end. Above this, there is no coexistence line, and the critical point has very special properties that has interested physicists for a very long time. Between a liquid and a solid, however, it's not possible to go from a liquid state to a solid state or to a crystalline solid state without going through a phase transition. And that is because as you are changing from a crystalline state to a liquid state, you are going from an ordered state with a specific distance and directions of ordering of the atoms or molecules to a completely disordered liquid. So there is no way, even if you increase the pressure a lot and then go back again, there's no way of changing between the liquid and the crystal without changing a phase. And that's why this point D is not really a point. This line actually extends as far up as you like. There is no end of this line. There is no way of going around this line like you can go around the liquid gas coexistence line. Now, Here's an example. The last was just a generic plot of a pressure, temperature, phase diagram. Now we've put numbers in for a specific substance, and this substance in this case is carbon dioxide. You've already done some experiments with carbon dioxide. You did this at a pressure of 1 atmosphere, so at very low pressure here, and the temperature was about 20 degrees. So you see that clearly you were far inside of the gaseous phase. In the bottle that you got the CO2 from, it's something like 80 atmospheres. That means that inside the bottle of CO2 that supplied your CO2 when you did your experiments, the CO2 was in the liquid state, and as you release the valve, it went through a phase transition and out came a gas that you used in your experiments. Now you see, if the temperature had been a bit higher, if the temperature of the gas bottle had been above 31 degrees, then the gas inside of the bottle would have been, say, at 40 degrees, it would have been here, it would have been a supercritical fluid, and there would be no phase transition in letting it out of the bottle. So here you see the critical point. Here you can read the temperature on this axis, that's 30.98, and you read the pressure of the critical point on this axis, 72.79. And the other unique point, as I said, is the triple point at 5 atmospheres and minus 56 degrees Celsius. So, as I said, you can read off any, if you know your substance and you know the conditions, you can read off on the scales on the pressure, for example, pressure and temperature, to determine what the state is. So you also did experiments using argon, and it's 1 atmosphere pressure. You see it. You did experiments at 300 Kelvin, which is far up here, which then means that it's far into the gaseous phase and far above the critical temperature of 150 degrees. Now I've just shown phase diagram in the pressure and temperature, which clearly shows the critical point as an endpoint of the gas-liquid coexistence line. Another way of showing a traditional phase diagram is to plot temperature versus density. In this case, at very low density, gases are low densities, and in this case we've got the gaseous phase down here at low density, and the liquid phase is here, and the very high density, that's the crystalline solid state. This diagram shows you that as you go from the vapor phase to the liquid phase at a constant temperature, there is a big jump in density. So when you're condensing your vapor to liquid, the density is changing abruptly to the liquid density. And the same as you are taking your liquid and you are freezing it For most substances, the density will increase when going from a liquid to a crystalline phase. Water to ice. So ice is one of the few materials where the crystalline solid state has a lower density than the liquid state. So what I'm showing here is a phase diagram in temperature and density that's not for water and ice. This is the more typical, the more generic form of a temperature density phase diagram. Now, so the line of coexistence between vapor and liquid that ended in which is this line, that ended in the critical point, is not a single line anymore. It's a because in between there is a region of densities where you have coexistence of vapor and liquid. But going up in temperature, you end up at the critical point at the top there. So this is the critical point and the critical density and a critical temperature. And in the same way, the triple point that was that's in the pressure temperature diagram, it's a unique point in pressure temperature space, now actually represents three different densities, because the three phases, liquid, gas and solid, that are in equilibrium at the triple point, all three of them have different densities. That's why there are three different densities at this triple point line, or triple temperature. And you've already been doing some simulations of the Lennard-Jones system. I have learned that actually it was probably a little bit premature to give you an exercise where you had to use the phase diagram of the Lennard-Jones system in order to see where you did the simulations. So next year we'll try to fix that. But now you see this is the phase diagram of the Lennard-Jones system. It has exactly the same shape as the generic phase diagram, with the gaseous phase, the vapor-liquid coexistence region, the liquid phase, liquid-solid coexistence, and the solid phase. And above here is a supercritical fluid phase, with the critical temperature and the triple temperature, and the temperatures and densities on the axis are now the reduced temperatures and densities. So this is temperature divided by the energy parameter epsilon, and this is the density divided by the length parameter sigma cubed. Now, the phase diagram of Lennard-Jones can be displayed in temperature on the vertical axis and pressure temperature as well. So, and here we see the triple point, the critical point, and the liquid-solid coexistence line that just goes on forever. So this is the Lennard-Jones temperature pressure phase diagram with the Lennard-Jones parameters on the axis. And here is the argon temperature pressure phase diagram with SI units. Well, not completely. This is in bars, but with on the axis. So, and you see that these two are very similar. And this is, and you might remember that you were asked to use argon to use argon properties for Leonard-Jones. And then the question is, well, you see that there are strong similarities between argon and Leonard-Jones. So how do we kind of map between them? Well, we can take one of them and put it on top of each other and rescale it and rescale the plot so that the critical points coincide or the triple points coincide. Well, the best is, of course, if both the critical point and triple point coincide. And here you see that the phase coexistence lines follow each other very nicely. And when we've mapped them over onto each other like this, you see that a temperature of 1 corresponds to a temperature of argon in Kelvin of 120 Kelvin, meaning that the epsilon parameter divided by Boltzmann's constant should be 120 Kelvin. And likewise, 1 on this scale gives a density of somewhere between 0.01 and 0.001. So by comparing the temperature scales there and there, when we've mapped them onto each other like this, we can then actually rescale it and get the parameters in Leonard-Jones for this for this gas, for argon in this case. And this is actually something much more generic. It's called the principle of corresponding states. And it means that if you've got two substances, 1 and 2, say Leonard-Jones and argon, then the state of 1 and you can take any state, any temperature of argon, for example, and you divide the temperatures by the critical temperature, you divide the pressures by the critical pressures. And you do the same for the state 2. So you divide by the critical temperature and pressure. And then you get rescaled temperatures and pressures that you can compare between the two substances. So when you've rescaled it, so this new value of temperature divided by the critical temperature has the same corresponds exactly to the state of this, which has the same value of T2 over Tc2. So this rescaling, you can do it with the critical, you can do it using the critical point or the triple point, or any unique state for that substance, any unique point. So in this case, for argon, the critical temperature of argon is 150 Kelvin. The critical pressure of argon is 4.86 megapascal. And here are the values for the reduced critical temperature of Leonard-Jones is 1.32, and the reduced pressure is 0.28. And here you see, when we then use the principle of corresponding states, that the critical temperature of argon divided, so we say that this critical any temperature divided by, or the critical temperature of argon should correspond to the critical temperature of Leonard-Jones. This gives us a value for the energy parameter of Leonard-Jones from the principle of corresponding states. And as you said, when I just showed you here, I said, well, here is 1 and that's 120, so this is a little bit quick, but maybe if here we've mapped the triple point, if I'd moved it a little bit to map the critical point, it would have corresponded to an epsilon of 113 Kelvin. And likewise, we can do it exactly the same way with the pressures. So the pressure is rescaled by the cubed of sigma divided by the energy parameter. And then we'll get from using the corresponding states that this pressure of argon corresponds to the critical pressure of Lennard-Jones. This gives us the length parameter of the Lennard-Jones unit for argon of 3.8 angstrom. Now, phase diagrams are not always as simple. What I've shown you so far are the generic solid, liquid, gas phase diagrams. Solid, liquid, gas phase diagrams always have a liquid gas critical point ending. So with this coexisting line ending in the critical point, and it has a coexistence line like this, and they end in the triple point. So for solid, liquid, gas, this is quite generic, and there is only one liquid state and only one gas state. However, you can any solid can have normally many different crystalline states. Ice, for example, actually comes in at least 11 different crystalline orders. And this means that when you change the pressure or temperature of ice, when ice gets buried, for example, deep down in a glacier, for example, on Greenland, glaciers can be several kilometers deep. And then naturally the pressure becomes very high at the bottom of the glacier. So when ice is formed from snow at 1 atmosphere at the top of the glacier, at say below -20 degrees, then it's ice of type 1H that is formed. But as it is being buried deeper and deeper, the ice crystals go through phase transition to type 2, to type 5, to type 6. Well, that's if they go to very, very high depths. So phase transitions of solids and phase diagrams of solids can look much more complicated, but they are very useful to give us an information about what phase to expect at any temperature or pressure. So, or for any other type of state variable. Now, it doesn't only need to be temperature and pressure, or solid state, or different crystalline states. A phase is, in fact, a much more generic description of a system. So, if you have a system that has properties that changes abruptly from one state to another, it can often be useful to call that a phase change. For example, for a ferromagnet, we can plot temperature along this axis, and we can subject it to a magnetic field. And at a low temperature, if we have the field pointing one direction, the magnetization will be in one direction. If we change the magnetic field, that will change the magnetization of the ferromagnet. But as temperature is risen, then the disorder grows in the magnet, and above a certain temperature there will be no such change in magnetization with the magnetic field. So that means that this coexistence line between the phase having magnetization up and the phase having magnetization down ends at a critical point, meaning that you can change the magnetization by from one side to the other by heating up the ferromagnet and then changing the magnetic field and then cooling down again, and you've changed your magnetization without going through a phase change. This is because the two phases have the same symmetry, but the direction is different. So now another type of phase transition that's been much studied is the phase transition going from an ordinary conductor at higher temperature to becoming a semiconductor at low temperature. So normally without a magnetic field, there is a Curie temperature below which suddenly the semiconductor changes behavior from having resistance when you send through a current to having no resistance. And this phase transition, or this transition in behavior, is connected to how magnetic fields behave when they approach the superconductor. So at low fields but high temperature, magnetic fields will penetrate through the superconductor, through the ordinary conductor. But as it goes through the phase transition to become a superconductor, the magnetic fields will not penetrate into the superconductor. And this is the reason why one can have superconducting levitation and actually levitate a superconductor when cooling it down. But I'm mentioning it here because to show you that a phase diagram is a much more generic and useful thing to show changes in behavior of matter, and it helps us understand what state variables and how are important for the phase changes, and at which states to expect to find the different phases. Now, more recently, in the 70s and 80s, there was a lot of interest into liquid crystals that are elongated molecules that at some phases they can be isotropic liquids. So at higher temperature, these molecules will just behave as liquids. But when you cool down the temperature, and then they tend to order due to the form and due to the shape of the molecules, and they start making ordered states. So they are not completely crystalline in that they are fixed positions. They can still move, but they are ordering somewhat like the magnetic spins that order, but not completely. But in this time it's still a liquid, but with order. So one type of order is called pneumatic order, where they can move freely but keep their orientation. Then you've got a smectic phase, where there is also order in order in bands, and so that you've got layering of the phases, and depending on the shape of the crystals, no, of the molecules, you can have other types of phases. And once again, you see that the phase diagram is very useful in order to understand the properties of these materials. So going from the generic solid, liquid, gas phase diagrams to crystalline phase diagrams to more complex systems, in the later years we've seen lots of substances being characterized. People build and make nano objects from many different things. And here is an example of amphiphiles that have polar heads and non-polar tails. These are molecules that we find everywhere in our body. All our cells have membranes made up of amphiphiles, and the cells in our body have membranes that are in lamellar phases, so they are ordered like this. And the study of phase diagrams of these phases are very important, both to make new materials, but also to understand living tissue. And in this case, the pertinent state variables are temperature and concentration. And you see, for example, one can form theories for when do you get high enough, large enough concentration in order to start self-organized formation of new structures. And so one could call the phase transition from liquid to crystalline solid for a self-organization. The word self-organization is more often used for more complex phases, like, for example, these hexagonal phases, like lamellar phases, and so on. Here's another example of a phase diagram, but this is a phase diagram of a dynamic pattern formation. So it's an even more complex set of behaviors. It's a dynamic behavior, and we see here that now the axes of the phase diagram are different from the thermodynamic phases we are used to. But, for example, this phi is in fact the concentration. So this is logarithm of the inverse of the concentration of particles in a liquid. And along this side is is a state parameter that's related to gravity. So this shows us that state variables can be much more than pressure, temperature, internal energy, and entropy. A state variable is whatever describes best the change of behavior, change of state of the system we're studying. And so in this case, these beautiful patterns, they are produced by small particles that are, in this case, the particles can move around, and then there is gas and oil showing the dark and bright areas. In this case, the particles are so dense that they don't move anymore, but there's only gas that's moving into the porous media and displacing the oil. So I'm just mentioning this because at our department, the physics department, there have been only 2 centers of excellence in research. There is also a center of excellence in education. And these 2 centers of excellence are in the condensed matter physics department, or in the condensed matter physics section. One older and one that's existing now. And these are examples of complex pattern forming processes that are being studied, and where we're using the tools of thermodynamics and statistical mechanics in order to analyze much more complex systems. Another so nowadays there is a lot of research into what is called active matter. And here is an example of a phase diagram of bacterial swarming. So I showed you the liquid crystals beforehand, and this is an example of elongated bacteria that move around. So they are in some sense liquid crystals that have organization, but that can propel themselves, so they are dynamic. It's not just a fixed system, but all of these are moving around, and thereby they are creating a whole host of new behaviors. One is called swarming, that they move around as swarms and create patterns that can be discerned. And also here we see that we can characterize them using a phase diagram, in this case using the aspect ratio and the surface density. And as I said, this is a very active area of research. This is the front cover of Science, one of the most important scientific journals in the world, from March this year, showing the defect dynamics of liquid crystals of active materials. Also, Nature, the other most influential journal, shows that on the scale of our cells, and inside the molecules of our cells, they behave like the dynamics of what's driving cell migration and cell division are liquid crystal-like dynamic structures of liquid crystals. And so even inside the molecules of our cells, physicists work on describing the dynamics of the active matter that constitutes our cells. Here's an example of showing you what I mean by active liquid crystals. You see that they reorganize, they swarm, they form groups, and they have topological defects and vortex dynamics that change all the time, but can be characterized, for example, in phase diagrams. And Louisa, that normally teaches this course with me, she is active in studying this. Also, as I said, on a smaller scale, these ones here you saw and this was bacteria, but on a different inside our bodies, the cells, they move much more slowly, but they do move around. They are active ingredients, and and we can characterize this as well as cell migration as an active agent that is deforming. One can study it using physics models to see how they swim. Or here is an example of a phase diagram of cell migration, where this time the axis of the phase diagram is the contractility, which is a property of how active the cell inside of the cell is at contracting, versus how active the cell is at adhering to the surface. And in this way, one can characterize thousands of experiments of biologists using physics models to say that, well, this is in fact a phase of migration which is driven by feet that are actively adhering to the surface. And then when there's less adhesion, you have two other amoeboid modes, and they either are decided, polarized, which way to go by an active inside process or an outside process. So using physics on life science actually helps putting a quantitative, helps quantifying and making models for life science, and life science is one of the hottest sciences when the most things are happening nowadays. It's very, but the point is that we are using inspiration, we are using statistical physics, we're using thermodynamics and the same way of characterizing, the same way of making models and drawing phase diagrams in order to quantify also very complex systems like active matter and living material. So I'll just stop by mentioning that if these are things that interest you, then in the Master of Science Physics, the physics program, and the Physics Master of Science program, inside the direction of materials, nanophysics, and quantum technology, there is a direction called disordered and complex systems, where you can delve into more complex materials, complex behavior of both living and dead systems. Or you can likewise take the biological medical physics option with the biological physics specialization to specialize in the physics of complex living material. Another option is to do the computational science master and do computational physics.